Good afternoon and welcome to Webinar Wednesday and of course happy HTM week. Today we are joined by Daniel Benz, Managing Director at IMT Analytics. Webinar Wednesday would like to thank our sponsor, IMT Analytics, a world leader in the manufacture, distribution and service of gas flow analyzers. Now these high precision medical class 1 gas flow and pressure measurement instruments are capable of testing a wide range of medical devices such as ventilators and anesthesia machines, oxygen flow meters, pressure gauges and suction devices. They also offer test lungs for cost-effective and safe verification of ventilators and anesthesia machines for functionality and precision. In addition, IMT Analytics offers easy-to-use comprehensive PC software for their biomedical testing devices. Their industry-leading EasyCal calibration service makes it convenient for the customers to send their instruments for annual maintenance and calibration. Since 1999, their brand has been well known globally for dependable, high-quality products and services. So for more information, please visit imtanalytics.com. Now, just a quick reminder to please join us for our HTM Mixer being held at the Hyatt Regency in Milwaukee, Wisconsin from July the 31st and August the 1st. Now, our mixers are a slightly modified, smaller, shorter duration and less crowded event that still provides valuable continuing education, networking and vendor engagement opportunities. So for more information and registration details, please visit htmmixer.com. Also, a reminder to please save the date for our fall MD Expo, which will be held at the Renaissance Dallas Addison Hotel in Dallas, Texas, from November the 10th to the 12th. So join us for 3 days of education, networking, and the latest advances in medical technology products and services. Again, for more information and registration details, please visit mdexposhow.com. Now, before we get started, TechNation, here at TechNation, we proudly continue to celebrate the dedicated professionals of the HTM industry with our 3rd annual Tech Choice Awards, also known as the Wrenches. Now, these awards honor the outstanding individuals and innovations shaping the HTM industry. Nominations are open through August the 15th, and the top 5 finalists in each category will be revealed in the October issue of TechNation, with voting open from October the 1st through to January the 9th next year. Please visit onetechnation.com/tech-choice-awards for more information and to submit nominations. Okay, today's webinar is eligible for 1 CE credit from the ACI, and you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us here at webinar@mdpublishing.com. Let's kick off today's webinar by giving away a Swiss Force Meister multi-tool. So using the questions feature on your dashboard, let me know the answer to the following trivia question. May is Lupus Awareness Month. What color is associated with lupus awareness? I'll reveal the answer and our winner at the end of the webinar. We'll wrap up today's presentation as usual with a live Q&A, so please submit your questions anytime using the questions feature on the webinar dashboard. As I mentioned earlier, our presenter today is Daniel Benz. So Daniel, you may begin whenever you're ready.
All right. Hello, everyone, and happy HTM week to all of you. Thank you, Linda, for the kind introduction, and big thanks to MD Publishing for hosting this session today. And most importantly, thank you so much for joining us. We know how busy your schedules are, and we truly appreciate you taking time to spend this hour together with us. I hope this session will be both informative and practical, and that you'll leave with some helpful insight for your day-to-day work. Today, I'll be talking about mastering precision gas flow measurement and ventilator testing. So why is that important? Well, we all know that gas flow analyzers are often used in critical applications, such as calibration and of life-supporting medical equipment. The issue is that unsuitable measurement setups and settings on your gas flow analyzer can lead to significant measuring errors. And at the end of the day, this might have an impact on patient safety. So that's why the aim of this webinar session is that you will learn how to set up and use your gas flow analyzer properly to ensure precise measurement and to minimize risks of measuring errors. So let's have a look at the agenda for this session. First, I will be talking about some general handling considerations for gas flow analyzers. Then we'll introduce you to 4 steps to take before you start your measurement. After that, I'll be giving you 3 tips to help you minimize your measurement errors. And finally, of course, we'll have some time to discuss all your questions you may have. Okay, before we dive into this, a quick poll for all of you. And the question is, in your current role, are you involved in ventilator and anesthesia machine testing? So I think the poll should now be visible for you.
Yes, we'll just give them a couple of seconds to
All right.
vote. Okay. Okay, right, I'm going to close the poll. Okay, you have 83% that say yes, and 17%, yeah, 17% say no.
Okay, perfect. Thank you so much for your participation. That's really good that we have a lot of people here that this content should really be relevant. But I hope it's also going to be informative and helpful for all the others that might come in touch with ventilator testing later in their career. Okay, so let's kick things off with some general handling considerations for gas flow analyzers. To ensure accurate measurement and guaranteeing longevity of your gas flow analyzer, there are 3 general handling considerations I would like to share with you. The first one is to protect the flow channels from contamination by applying the protection caps. You can see one here in this picture on the flow channels whenever they are not in use, and to always use the included dust filter in front of the flow channel when a flow channel is in use. This is really crucial for all gas flow analyzers in the market. Please also ensure that you have a dedicated filter for your analyzer and that you never use it in reverse direction, means that the dirt side is facing the flow channel of your analyzer. Secondly, please ensure that your device is being calibrated and serviced as per the manufacturer's recommendation. Most gas flow analyzers are on a 1-year calibration and maintenance schedule, and it's of highest importance that the accuracy of your measurements are being verified frequently. And lastly, make sure that you use the original case or bag to transport and store the device in order to protect it properly. These are high precision measurement instruments that must be handled with care. Okay, so that was it about the general handling considerations. Now let's dive into the 4 steps to take, you should always take before you even start your measurements. So the first point is to allow warm-up. This is to avoid that you take measurements while the sensors of the devices are still undergoing some warm-up related temperature drifts. It's important that your gas flow analyzer, but also your device on the test, are both warmed up before you start taking measurements. Warm-up times of analyzers and ventilators can vary by device. So in most cases, the manufacturer specifies the required warm-up time, warm-up period in the user or the service manual of the device. If you can't find such kind of information, a good practice value would be 30 minutes. Then pretty sure you're on the safe side. The second thing to consider before you start measuring is to perform the necessary calibrations on your gas flow analyzer. So depending on the application and the device you use, the following calibration should be performed. First and most important, a zero offset calibration. This applies for any measurement task and should always be done. The purpose here is to avoid that we take measurements with sensors that have drifted. That's why it's crucial to perform the zero offset calibration after the warm-up of your device. So we'll zero out any drift that happens during the warm-up of the devices. As you can see in this illustration here on the slide, particularly an offset on the flow measurement must be avoided as it amplifies as error in the volume calculation, because volume is actually mathematical integration of the flow signal over time. So if you have an offset on your flow signal, it's going to amplify over time in your volume measurement. Then second point here, calibration of an oxygen sensor if you are using one. Some gas flow analyzers have one built in, some have a separate module for that. So that oxygen sensor should be calibrated as well. And lastly, there might be peripheral sensors that you are using that need calibration as well. So for example, this could be an anesthetic gas concentration sensor that requires a zero offset calibration too. Okay, number 3 on the list is to check your setup. We often see that measurement setups can be quite complex, and ventilator manufacturers sometimes don't do a great job in explaining the setup with supporting pictures. And if they do, it's most likely just for one specific device they have once selected for whatever reason. Here's an example for that. Here are 2 measurement setup pictures from a service manual of a ventilator manufacturer. The pictures are actually pretty good, even though, for example, this teed-in pressure here is quite hard to see. The issue here is that this quite complex setup is based on the specific gas flow analyzer they selected for this picture. As you can see, it consists of multiple parts. We have flow module, we have measurement module, so we have an O2 sensor module as well. We have a trigger cable that goes to the ventilator in this picture here. And this is all based on that specific device. So what if you want to use a different analyzer? In such cases, this manufacturer just leaves it to you to figure out how your setup has to look like. Here's a second example. Again, the picture here is based on a very specific model of analyzer, but the picture doesn't clearly show which ports are supposed to be used of this gas flow analyzer here. So if you use a different one, you'll need to figure it out yourself again. And depending on the analyzer you use, this can look very different, eventually involving teeing in pressure, as we've seen in the previous example, or, for example, an oxygen measurement module. Here's the third example. This is a great one. In this case, there is only a very basic description of the setup, and everything else you need to figure out yourself. So, of course, we can't expect ventilator manufacturers to add setup pictures for each and every gas flow analyzer available on the market. Therefore, it is very important for you to understand your gas flow analyzer that you use in your daily business, because depending on the analyzer you use, your measurement setups can look very different. For example, the setup we've seen in the picture before, here on the left-hand side, can look as simple as in the picture on the right-hand side with a different analyzer. In this example, it is our, here in the example on the right side is our Citrix H5, which is a so-called all-in-one device that measures all the relevant parameters right inside the flow channel, allowing the simplest possible setups. Often you will also find setup-related considerations in the user manual of the analyzer. So make sure you know how your gas flow analyzer measures the relevant parameters, and check the user manual for setup-specific information. It is really crucial to understand, for example, what is being measured inside the flow channel of your analyzer, and maybe even more important, what is not, because wrong setups can really lead to significant measuring errors. All right, we talked about warm-up, calibrations, setup, and the last point here is to check your settings on your gas flow analyzer. And this is a very important and slightly more complex topic. So I'd like to give you some background information here to help you better understand its relevance. So don't worry if parts feel a bit overwhelming here. I'll always highlight the key takeaways. And the good news is also TechNation webinars are recorded, as you may know, so you can always rewatch the session later if needed. All right, let's dive right in here. The most important settings on your gas flow analyzer are gas type and gas standard. These two settings are crucial for all flow and volume measurements. The third one we're going to discuss is trigger settings. Trigger settings are relevant when we want to measure the so-called breath-based parameters, such as a PEEP pressure, a respiratory rate, or for example, a tidal volume. And last but not least, it's the measurement parameters themselves that we can configure on our gas flow analyzer. So gas flow analyzers can measure many different parameters. So we must ensure that we look at the right measurement and have it set up with the correct unit of measure. Okay, before we dive into these settings, I would love to hear from you again with a quick poll. The question here is, are you guys familiar with the term gas standard? Please participate now, yes or no.
Okay, we'll give them a few seconds. Okay, oh, it's close. It's close. Okie dokie, I'm going to close the poll, and we are at 59% yes and 41% no.
All right, good. It's good that it's at least more than 50% yeses here. Thank you so much for your participation. And now let's bring that value to 100%, as the gas standard is one of the most, if not the most important setting on your gas flow analyzer. So let's jump in here. So the question is, why do we need to set a gas type and gas standard on our gas flow analyzer? The reason is that volume that is occupied by gas is dependent on several different factors. So let's assume here on this slide you see a container, and let's assume we can capture some room air in that container with a movable lid, and let's call that V0 for volume 0. What happens if we increase the temperature of that volume of air? The answer is it's going to expand and occupy a greater volume. The same applies when we increase the humidity of the gas. On the other hand, as you all know, we can put gas under pressure and we compress it so its volume decreases. And as last example here, if we increase the level of oxygen in our gas, the volume is going to expand as well. So that means that the same number of gas molecules occupy a different amount of volume depending on gas conditions and the gas characteristics. Because of that, gas flow analyzers need to know many different parameters for the flow and volume calculations. The first three here on the list, gas density, viscosity, and viscosity coefficient, are defined by a gas type setting on your gas flow analyzer. So we need to tell the device or analyzer if we want to measure flow and volume of air, or for example, oxygen or CO2. So there's a bunch of different gas types that we can select from, and this then defines the gas density and viscosity. You will find that setting on any gas flow analyzer. The other parameters are typically being measured by the gas flow analyzer, for example, gas temperature, the gas pressure, and the oxygen concentration. So with all these set and measured values, the gas flow analyzer can then calculate the actual flow rate of gas passing through the device. And we consider this process gas flow measurement. In order to understand the meaning of a gas standard, we first need to understand the separation between gas flow measurement and gas flow displaying. And we've seen in the previous slide, gas flow measurement is based on the actual gas conditions. This is typically called the gas standard ATP. That stands for actual temperature and pressure. So in order to make flow rates comparable and independent from gas conditions, flow rates can then be converted and displayed in a different gas standard at standardized gas conditions. For example, how much of flow would that be if the gas was, let's say, 40 degrees Celsius of temperature and 90% humid, even if it wasn't at the time we measured it. And we consider this process gas flow displaying. So we have a separation between what we measure and what we display. So now you might ask, why do we need to care about that? So let me talk about the practical part of it. So what you can see here on this slide is a typical ventilator setup on a patient. We have the ventilator, then we have a circuit system with a humidified and heated inspiratory limb. We have an interface to the patient and with the Y-piece, and then we have an expiratory limb back to the ventilator. Let's assume that this ventilator delivers a volume of 500 milliliter measured at the output of the ventilator by its internal sensors. And let's assume that this is dry air from a compressor system that has a temperature of 21 degrees Celsius. What happens to that volume of gas while it travels through the inspiratory limb until it reaches the Y-piece at the patient site? Well, the temperature and the humidity of the gas are going to increase because we have a humidifier and a heated wire. So what is the consequence of that? The volume is going to increase as well. So this means that in our example, the volume that actually reaches the patient is no longer the 500 ml delivered by the ventilator, but is now approximately 560 ml because the gas temperature at the Y-piece is, let's say in this case, typically 37 degrees Celsius and has a humidity of 100%. So what ventilator manufacturers usually do is that they compensate for that with their setting and monitoring on the device, as they can all calculate this through gas standard conversions. So in our example, the setting and monitoring value on your ventilator you would typically see in this situation is not the 500 ml delivered to the circuit system, but the 560 milliliters that ends up being delivered to the patient. Okay, so they compensate for that. As 37 degrees C is also the typical body temperature, the gas condition at this temperature and 100% humidified is called BTPS gas standard, stands for body temperature and pressure saturated. I'm pretty sure that many of you have heard this term because most ICU ventilators actually display settings and measurements on their device in the BTPS gas standard to reflect the volumes that are actually reaching the patient. So what's the issue here? Well, when we test such kind of a ventilator with a gas flow analyzer, the test setup typically looks like this. So we have circuit system, Y-piece, our analyzer, and then a test lung. And in such a situation, it can then easily happen to you that you set up a tidal volume of 560 milliliters on your ventilator, but you only measure a VTI of 500 milliliters on your gas flow analyzer. So how can that be? Well, assuming that the ventilator setting is using the gas standard BTPS, this means, as we've learned earlier, that it's going to underdeliver in volume because it considers an increase of the volume in the circuit system in a real patient situation, as we have a humidifier and a heated inspiratory limb, and that volume is going to increase while it travels along the circuit system until it reaches the patient. But unlike in our previously discussed patient setup, in our test setup, the gas condition is not going to change, as there is no humidifier nor heated inspiratory limb. And therefore, our gas flow analyzer then measures just the 500 ml actually delivered by the ventilator. And if that analyzer is then set to the gas standard ATP, means it considers the actual temperature humidity for the flow calculation, it also displays just the 500 ml as VTI. So what we do in this example is actually comparing volumes in different gas standards, BTPS on the ventilator versus ATP and the gas flow analyzer. And as you can see, that can lead to significant errors. So how do gas flow analyzers tackle this problem? Well, they let you display flow and volume in different gas standards. And the only thing you really need to remember from this part of theory here is that the gas standard setting on your gas flow analyzer must always match the gas standard used by your device under test. In this case here, or in our example, the ventilator. Different ventilator manufacturers may use different gas standards. The most common ones are called BTPS, as already mentioned, and you will also see STP, for example. And the only thing you really need to figure out is the gas standard used by the device under test, and then set the same gas standard on your analyzer. Most manufacturers specify the gas standard in their technical documentation, maybe service manual or user manual. Otherwise, they will be able to tell you when you ask them, or maybe you hear it when you go through service training. Okay, back to our example. If we have our gas standard on our gas flow analyzer matching the one used by the ventilator, the displayed volumes should then match, as we are now comparing apples with apples, or in these guys' case, maybe more banana with banana. All right, before we talk about the next important settings, let's quickly recap the most important takeaways here. So number one is to make sure that you set the gas type on your analyzer to the gas you're actually measuring. And number two is to set the gas standard on your gas flow analyzer to the same one used by your device under test. Okay, next up, let's talk about trigger settings. So that's another critical setting on your gas flow analyzers. So trigger settings are used by gas flow analyzers to identify the breath phases, inspiration and exhalation of an ongoing ventilation. In most analyzers, you will see the terms start and stop, or also called end trigger. This relates to the inspiratory phase. So the start trigger is used to determine the start of an inspiration phase, while the stop or end trigger is used to detect the end of an inspiration phase, what also indicates the transition from inspiration to exhalation. And with the next start trigger, actually a next breathing cycle starts. So trigger settings are necessary for the gas flow analyzers to calculate the so-called breath-based parameters, such as tidal volumes, a respiratory rate, or something called PEEP, which means positive end expiratory pressure. These are all parameters that are kind of related to the breath phases. And without triggers, gas flow analyzers can't measure these parameters and typically don't display them or indicate something like no trigger on the screen. And most gas flow analyzers also have a trigger indicator on the display that actually indicate each time when the analyzer is being triggered. For example, you will see later in the demo on IMT Analytics analyzers, there is a T flashing up on the display whenever a trigger is being detected. So if you don't see the trigger indicator, and if your analyzer is not able to measure the breath-based parameters, this means that your trigger settings are not suitable for your current application. So we've just learned that our gas flow analyzer needs to be triggered in order to be able to measure breath-based parameters. But even if your gas flow analyzer is triggering, inappropriately set trigger settings for your specific application can have significant impact, for example, on tidal volume accuracy. Because, for example, as you can see in this slide, the inspiratory tidal volume, VTI, is calculated by mathematically integrating the flow from the start trigger to the end trigger of an inspiration phase, right? Volume is flow over time. So it starts for the VTI at the start of an inspiration till the end of an inspiration phase. And ideal trigger settings are as close as possible to the real breath phase transition. So it should actually be here and then here. And as you can see in this graphics here, these triggers are a little bit delayed, and this will have an impact on our tidal volume calculation, because a little portion here at the start of the inspiration is being lost here because our trigger is too late, and afterwards, after the inspiration phase, because our end trigger is too late as well, a little portion of our exhalation is being calculated as negative or considered as negative volume deducted from the calculated VTI. So that means our calculated VTI by our gas flow analyzer in this example will be significantly too low. Okay, before we talk about how we can determine suitable trigger settings, let's talk about some basics about trigger settings first. So trigger settings are typically defined by three main parameters of settings: a trigger source, a trigger signal, and a trigger level. So the trigger source defines the physical interface for the trigger. In this example, this could, for example, be a measurement in one of the flow channels of the device, but it could also be a pressure port of the analyzer. Most analyzers also offer the option to use an external digital trigger signal as trigger source. Then the trigger signal defines which signal shall be used for triggering. Here you can typically choose between the pressure and the flow signal. For example, if you have an analyzer that measures the pressure inside the flow channel and you want to use that signal for your triggering, then you would select the flow channel as trigger source, and then the pressure measurement inside the flow channel as your trigger signal. Finally, the trigger level defines the threshold value of the trigger to be activated. In addition to the threshold level itself, you will also need to define whether the trigger shall be activated when this threshold is reached on a rising or a falling edge of the trigger signal. So the first and main challenge with trigger settings is to find a good trigger signal for our trigger levels. The question is, what characterizes a good trigger signal? So the answer is, a good trigger signal allows trigger levels to be set as close as possible to the timing of the real breath phase transitions. That sounds logical, right? When your breath detection of your analyzer is as close as possible to the reality, it will be able to measure breath-based parameters as accurately as possible. But what does that mean specifically? Let's have a look at some example signals here and judge their qualification as a good trigger signal. And what you can see here on the screen is a first example. So the dashed vertical lines, you can see here, the gray ones, indicate the real start and end of an inspiration phase. So this is actually where we would ideally to have the trigger levels or trigger set in our gas flow analyzer. The gray area around the zero flow line here indicates an area where we don't want to have our trigger levels, as a little bit of signal noise could create some false triggering. So we want to keep it a little bit higher or lower there, not in that gray area. So let's see if that's a good trigger signal. It actually turns out that it's not, and here is why. The first part actually looks great. As the flow signal is rising rapidly here, we talk about a steep slope of the waveform. We can nicely set a start trigger quite close to the area we want to avoid on a rising edge of the signal, and sufficiently capture the start of the inspiration phase with our analyzer. However, there is no way here to set a sufficient trigger for the end of the inspiration phase. The flow signal is just too flat here in this area, and the changes of the signal are within the zone we can't properly trigger without risking false triggering. So if we would set the end trigger to the same level as our start trigger, close as possible to the gray area on a falling edge, we will have a huge mismatch between the real breath phase and the breath phase detected by our analyzer. So this is not what we want. So again, this is not a good trigger signal. So let's have a look at the second example to understand this topic a little bit better. So how about this one? Let's see how this one looks like. So here, it turns out that it's quite good, because here we have a positive flow through the flow channel in the inspiration phase and a negative flow through the flow channel of our analyzer during the exhalation phase. And this is a very typical situation in ventilated testing applications. As our flow waveform has quite okay steep edges here or slopes, we can then set a start trigger on a rising edge of the flow signal here, quite close to our gray area on a positive level, and then the stop trigger on a falling edge on a negative flow value here. And this lets us quite accurately detect the real breath phase, as you can see in the graphics. However, the signal slope is not as steep as in our previous example. So that means that our trigger settings are a little bit delayed compared to the reality. What does that mean? So for our timing parameters like inspiration time or a rate measurement, it doesn't have significant impact because it's just a little bit shifted in time, right? But as we have seen in one of the previous slides, this is going to have a little impact on our volume calculations. Because again, here, if we take a look at the inspiratory tidal volume, for example, which is that shaded area underneath the flow curve, we are going to miss a little bit here at the start of the inspiration phase. And then it's going to consider a little bit of our exhalation flow already still in our inspiration time. So that means it's going to be deducted from our volume calculation, what leads to the fact that our calculated tidal volumes here are not going to be 100% accurate. So overall, we can say that this is a quite good trigger signal, even though it could be even better if the slopes of the waveform were steeper at the beginning of the two breath phases. Last example, how about this one? So this one is actually perfect, right? Because here we have very steep rising and falling edges or slopes of the signal, right where our real breath transitions are, makes it easy to set trigger settings perfectly in sync with the reality. So our lessons learned here from these three waveforms you've seen, a good trigger signal has a steep rising or falling edge or slope at the beginning of each breath phase. So that all sounds a little bit challenging, right? So let me ask you this as our next poll question for the ones of you that actually are involved in ventilator anesthesia machine testing. Have you ever touched the trigger settings on your gas flow analyzer? Please vote now.
Okay. Looking close again.
All right.
Yep, okay. Right, I'm going to close the poll. And you have got 44% said yes and 56% said no.
Okay, thank you so much. That's very interesting. And it's not that surprising to me that many or the majority of you have never had to touch the trigger settings, because the good news is that most modern, at least, gas flow analyzers have default trigger settings sets, for example, for adult, pediatric, and high frequency ventilation. And these triggers will work well in 95% of your applications where you have a positive and negative flow through the flow channel of your analyzer. And in most testing applications for ventilators, you will have a positive and negative flow through the flow channel of your analyzer. So here on this slide, you can see typical flow and pressure waveforms on the left-hand side for pressure-controlled ventilation, and on the right-hand side for volume-controlled ventilation. And in both cases, the flow signal typically has very rapidly rising and falling edges at both breath transitions. And also, and this is actually what we just learned earlier that is most important for a good trigger signal, right? Additionally, the baseline of the signal typically doesn't change depending on the ventilation settings. So no matter what inspiration pressure or what tidal volume I've set up on my ventilator, at the start of an inspiration phase, I typically have the flow rising from 0 up to a higher positive level of flow through the flow channel. And at the beginning of an exhalation phase, the signal crosses the zero line of flow and transitions to a higher negative level of flow through my flow channel. Okay, so this means that the flow signal in the flow channel and with a start trigger level at a low positive number on a rising edge and a low negative number on a falling edge of the signal for the stop trigger typically works perfectly fine. And this is why these here you can see on the slides or very similar trigger settings are typically the default trigger settings of your gas flow analyzer. That explains why most of you maybe haven't ever had to touch the trigger settings. So we've learned that the default trigger settings work well in most applications as long as you have a positive and negative flow through the gas flow analyzer, and that these trigger settings are then independent from your ventilator settings. So the bad news is that this is not always the case, and that might explain why some of you had to touch the trigger settings. So let's have a look at such kind of a situation as an example where it gets a little bit more challenging to find suitable trigger settings. In this example here, we have a ventilator in BiPAP mode and that applies pressure on two different levels to a test lung. And the test setup is equipped with a defined leakage in front of the test lung to simulate a typical patient interface with a non-invasive ventilation interface, for example, a mask with a leak. In this application, there is no negative flow through the gas flow analyzer during the exhalation phase, because all the volume that comes out of the test lung is going to leave here through this leakage. And therefore, the flow in the flow channel of our analyzer never goes negative. And that means that our previously discussed default trigger settings are no longer going to work. A typical resulting flow waveform in such an application is also not a suitable trigger signal due to the lack of a steep falling edge at the end of the inspiration phase. On the other hand, the pressure waveform looks pretty good as a trigger signal, as it features steep rising and falling signal edges at the beginning and the end of inspiration phase. So let's have a look at the pressure curve and see how we would set the trigger settings here. So in BiPAP ventilation, the upper pressure level is called IPAP and the lower pressure level is called EPAP. And in such a situation, we would then typically set the start trigger level to EPAP plus 1 centimeters of water pressure on a rising edge and the stop trigger on IPAP minus 1 centimeter of water on a falling edge of the signal. And that ensures triggering, quite accurate triggering in this example. However, the challenge here is that the pressure levels are going to change when we change the settings on our ventilator. So let us have a look at that in a real life situation. So now I'm going to change my camera a little quick. First, I'm going to stop sharing here. And let me show you what I have on my table here. I have a camera that can move around. As you can see, I have a little ventilator here, and that one is connected to my analyzer here. It's a Flow Analyzer Pro. Then I have my circuit here that goes to the test lung, and here you can see this defined leakage in front of the test lung. So now let's have a look at our gas flow analyzer. So I'm going to change the camera again. We can see the display of our gas flow analyzer. So you can see the settings I have now on my ventilator is an EPAP of 3 centimeters of water and an IPAP of 6. And as you can see right now, my analyzer is not able to measure the breath-based parameters, for example, IPAP rate and I/E ratio. This is because right now I'm running on the default trigger settings that we have discussed earlier that are based on a negative and positive flow through my device, which I don't have in my situation here. So here, as we've learned, we would use the pressure curve and set our triggers. So on this analyzer, in the settings, I can go into the trigger settings, and I will tell the device now that I want to switch from my flow waveform to my pressure waveform. And I'm going to set the level for the start trigger to EPAP plus 1. EPAP is 3, so I'm going to set it to 4 on a rising edge. and I'm going to set my stop or end trigger to IPAP -1. IPAP is 6, so I'm going to set it to 5, and also pressure. I'm going to set it to 5 millibar or centimeters of water on a falling edge. So as soon as I have applied these settings, now I can see that my gas flow analyzer is able to measure my breath-based parameter. And you can see there is a T flashing up at the right corner, in the right corner of the screen when a trigger is being detected. What is the case now? So now I can measure my breath-based parameters. So let's assume that this was the first setting I had to check on this ventilator, IPAP of 6 and EPAP of 3. And let's assume the next setting set is IPAP of 10 and EPAP of 5. So I'm just going to change that on my ventilator here a little quick. So my next settings are IPAP of 10 and EPAP of 5. And what you will see as soon as I apply these settings, now you can see the pressure level is higher. So I have a EPAP of 5 and IPAP of 10. And suddenly you can see my gas flow analyzer is no longer able to trigger. So there's no trigger indication visible anymore. Why is that? Because my start trigger is now on a level below my EPAP. So my analyzer is no longer triggering. So what I would have to do here to resolve this is I have to go into my settings and move my trigger settings up along with my IPAP and EPAP settings. So my EPAP is now 5, so I'm going to set my start trigger to 6, and my IPAP is 10, so I'm going to set my stop trigger to 9. And as soon as I did that, I go back to my measurements. You can see now the gas flow analyzer is again able to trigger and can again measure the breath-based parameters. All right, let me switch back here a little quick and share my screen again. So yeah, that was it about trigger settings. I know it's quite a complex topic, but as you can see, as you saw in this example, in some applications, it's really crucial to understand the meaning of the trigger settings and to know how to find suitable trigger settings for a specific application. So last but not least, on the settings side is that we want to ensure that we look at the right measurement and have it set up in the correct unit of measurement, matching our device under test. So be aware that ventilator and test equipment manufacturers sometimes use different terms for exactly the same thing. For example, one ventilator may use a term called P-peak for the maximum pressure during the inspiration phase, while another device would probably call it PIP, which stands for peak inspiratory pressure. Or one ventilator could use the term rate for the breath rate, while another device might use the term frequency. So gas flow analyzers can typically measure up to or more than 25 different parameters. So further, they can usually display them in multiple different units of measurement. For example, pressure could typically be displayed in centimeters of water, millibar, PSI, or Pascal. Going through all of them would be a topic for a future education session, but it's important that you understand the capabilities and terminology used by your analyzer as well as your device under test in order to configure your measurement parameters on the analyzer appropriately, matching the compared values on your ventilator. All right, so these were the 4 steps to take before starting your measurement. Allow warm-up, perform the necessary calibrations, check your setup, and most important here, check the settings of your gas flow analyzer. Okay, let's shift gears here a little bit and talk about the last main topic, the 3 tips to help you minimize measurement errors. And I'm going to show that to you on my Flow Analyzer Pro here. So I'm going to stop sharing and switch my camera again so that you can see my analyzer. First of all, if your gas flow analyzer offers this feature, it's highly recommended to create and use profiles for your specific applications. So on modern gas flow analyzers like our Citrix H5 or this here, the Flow Analyzer Pro, you can create profiles and save all the critical settings that we've discussed earlier in a profile for later use. So your gas type, your gas standard, your trigger settings, and all kind of screen customization. So on most gas flow analyzers, I can customize exactly what I want to see on my screen. Here, even I can customize the color of my measurements, which is sometimes very helpful to see what value, to find the value I'm looking at quicker. And all these customizations on this device, for example, I can save as profile. So whenever I have a specific application, for example, a specific ventilator, and I've gone through the exercise of figuring out what gas standard, what trigger settings I have to use, once I configured all my screens exactly as I want to, I can then save that and name it as a profile. And next time when I have the same application again, I can just reload this profile and everything is set up the same again. So using profiles helps minimizing the risk of inappropriate settings and reading errors. The second practical tip is to use advanced automation and aids as features that your gas flow analyzer might offer. So watch out for things like real-time waveform analysis, as you can do here on this device. For example, if I enlarge my pressure waveform here, I can see it on the big screen here, and I can even pause my waveform and then measure values here. So this can be very helpful if you really want to find a suitable trigger signal and to see what trigger levels makes most sense for my application. Additionally, you might find help for your trigger settings. Maybe you've seen that earlier when I changed the trigger settings. On this device, I have a graphical indication of my trigger settings, which is sometimes extremely helpful to understand what exactly you're triggering on, which curve or which waveform, and on what edge of the signal. So this can really help you find suitable trigger settings easier and understand what you do. And last but not least, on this device here, on our Flow Analyzer Pro, we also have something called automatic trigger detection. So what I can do here is I can set my whole trigger setting to be completely automated. So what the device is doing now is it analyzes the pressure and flow waveform in real time and finds suitable trigger settings for me. So as you can see, it's triggering now with my current settings. And if I switch back to the previous settings we had with an IPAP of 6 and an EPAP of just 3, you will see that once I apply these settings and the waveform changes, remember earlier, because we changed the settings of our ventilator, we had to amend our trigger settings, but now the device has done that automatically. So it's still triggering, and you can see we have accurate readings of our breath-based parameters here. So this is extremely helpful in situations that you have to kind of find your own trigger settings. And the last practical tip I wanted to share with you is actually a feature that is offered by advanced state-of-the-art gas flow analyzers, which actually addresses all the challenges we have discussed today. It's to use ready-to-use ventilator-specific testing applications or test sequences. So what we do on our devices, our latest devices, Citrix H5 and this Flow Analyzer Pro here, is we build, together with the ventilator manufacturer, we built their service procedure into a guided app on our device. So we have a library of them already, and that's going to grow over time. And these apps actually guide you through the testing. So we have a demo application I can show you here a little quick. So they show you how to set up the device with that specific analyzer you're using. Then it's going to help you with things like settings on the ventilator. When it comes to take measurements, like on the next page, I'm just going to change the settings of my analyzer here a little bit so that we have values that make sense. When it comes to take measurements, these apps know actually which parameters we need to test, and it knows the expected ranges. It can also calculate sometimes expected ranges. With some ventilators, this is based on an actual measurement. So it does that automatically and gives you pass-fail criteria on the screen. Sometimes it's just to confirm things. It depends on the exact procedure of the manufacturer. At the end of the application, you can then add information about your device under test and about yourself, and you can even sign a report here. And then that all goes into a report that you can download as PDF file from the device. So as you can see, this actually makes testing workflows more efficient and it eliminates the risk of measurement and transcription errors, but it also ensures that your device is set up correctly, because things like gas type, gas standard, trigger settings are saved for that ventilator and are being loaded automatically when you start the app. All right, I'm running a little bit longer than expected. Sorry about that. So I'm just going to get back to you guys and share my screen again for the key takeaways. So let's summarize what we have discussed in this session. So number one key takeaway is ensure that you allow warm-up of your analyzer and your device under test, and after that perform a zero offset calibration on your gas flow analyzer before you start taking measurements. Number two is that you need to understand the features of your gas flow analyzer. So be aware what is measured inside the flow channel, for example, and what not, and make sure that you understand the setup related considerations for your specific device. Number three is to pay special attention to have the appropriate settings on your analyzer for your specific application. As you've learned in this session, this is very important. And if there's one key takeaway that I want you to keep from this session, then it's the gas standard. Set the gas standard same as on your device under test. That's really most important. And last but not least, take advantage of advanced features that your current or future gas flow analyzer can help, that they offer to reduce the risk of measurement and reading errors. Okay, that wraps it up. I hope this was helpful for you. Thank you so much for your participation. I hope we have time for one question at least. Otherwise, I'm going to be answering all the questions that you entered. I think they're going to send it to me after this session. Thank you so
We have
much.
got time. Yes, we've got time for one we can squeeze in, Daniel. Is one that's come in says, does a depleted O2 sensor in my analyzer affect the accuracy of flow measurements?
Yes, it does. Particularly, not necessarily, I have to say, as soon as you have the gas type, typically you will find the gas type on your gas flow analyzer saying air O2 automatic. And as soon as it says O2 automatic, means that the actual measurement of oxygen with the sensor is being considered for the flow calculation. And if that one is not accurate anymore, that can have a slight impact on your flow accuracy. If you set it to air O2 manual, and then you set, for example, 100% oxygen, then it's not going to take the sensor into account. Then you can kind of rule that out. But yeah, that's why it's important to replace the sensor if it's depleted and to calibrate it from time to time.
Perfect. One more we can squeeze in. Is it possible to set the start and the end trigger on different signals?
Yes, most analyzers allow that. So you can, for example, if you have like very specific or special situations where you see, oh, my pressure trigger is perfect for my start trigger and my flow trigger is better for my stop trigger, you can even on most analyzers, you can set a start trigger on the pressure curve and a flow trigger on the flow waveform.
Perfect. Thank you so much, Daniel, for a great presentation. I'd like to encourage everyone to visit IMT Analytics website to learn more about the products they provide to the industry. So please visit imtanalytics.com. Now, as promised, the answer to today's trivia question is purple. So congratulations to our winner, Ryan Barry in Michigan. And just a quick reminder, you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Now, if you've missed any of our past webinars, including any by IMT Analytics, please visit webinarwednesday.live to view our whole webinar archive. We'll be back soon with another webinar, so visit webinarwednesday.live for more details and complimentary registration. So thank you once again for all your time today, and we hope you enjoy the rest of your day.
Thank you. Bye.